30 seconds, VTC 6HTBO 3150. Ten, 9, 8, 7, 6, 5, 4, 3.
Looking through your skin is the title of this lecture. Now, you can't actually look through your skin, except perhaps through very thin sections of it. For instance, in one of the last lectures, you looked through the lobe of my ear. But looking through the skin must have been an ideal of doctors ever since doctoring started. Now, the reason we can't look through our skin is that we are reasonably opaque to ordinary visible light. That is a light to which our eyes are sensitive. And therefore, if we want to look, we have to use radiations of different kinds. Now, what I'm going to tell you about this afternoon are 3 different methods of looking through our skin using really techniques which have little similarity to each other. Now, it is common when one is testing devices such as X-ray machines, which I tell you about, or gamma cameras, or ultrasonic scanners, to use something which are called phantoms. Those are models with inclusions of jelly and something else, for instance, so you can try out what kind of contrast you might get. And I've got 4 of these phantoms with me this evening, and I would like to introduce to you my 3 jelly babies, if they will allow me to call them that. Would you just like to stand up? And would you like to show your jellies to the camera? We've got a red jelly on my right, a pink jelly in the middle, and a blue jelly along the left. And when I say the colors, I mean there's an inclusion about the size of a tennis ball inside some clear jelly. Right? Thank you very much, jelly babies. You can sit down again. And I'll call upon you when I need you. Now, in 1895, a professor at a small provincial German university called Professor Röntgen discovered X-rays, or Röntgen rays as they were at first called. And he used equipment which is rather like that, which was rather like this here. Basically, it consists of a source of high voltage and an evacuated tube, about which I will tell you a little more in a moment, which has 2 electrodes inside it. Now, this experiment which I did just here, and I would, if I was really X-raying my hand, I would have had to hold my hand in front of this tube with a screen out here, so you could have seen the picture of my hand, is the only experiment in this series of lectures which is faked, which isn't working. And the reason that we haven't made it work is that it has been found out since 1895 that X-rays and other forms of ionizing radiations are dangerous to people and animals. In fact, they're dangerous to life. And if I had turned this X-ray tube on here, we would have produced X-rays in all directions, and we would have all have got a dose of X-rays. Now, people now go to very considerable pains to reduce the dose of ionizing radiations, that is, the rays like X-rays and the rays from radioactive compounds, to the absolute minimum. So there is a background of ionizing radiation from cosmic rays and from the natural radioactivity, from rocks and so on, impinging upon us all the time. So anyway, it is a policy now which is enforced by a body called the National Radiological Protection Service, that the irradiation of the population should be kept to an absolute minimum. Now, having said all that, I must also say, practically in the same breath, that in this program, we shall be using X-rays, and we shall be using small quantities of radioisotopes. But we've made absolutely sure, and the National Radiological Protection Service has confirmed this for us by making calculations and experiments, that the quantities of radiation which we are going to use are so negligible as to be even small in comparison with those which are permitted for demonstration and educational purposes. So nobody here need to be concerned about radiation dosage. But back to Professor Röntgen. The fact that photographic materials which had been left lying close to discharge tubes, that is, tubes which had practically a vacuum inside them and a high voltage applied to electrodes which were seated in their ends, had been known for some time. But nobody seemed to have really cottoned on of what use these might be put to. In fact, even Faraday, and his name appears to work its way into all my lectures, who worked at the Royal Institution, at one time of his life worked on discharge tubes. And one of the dark spaces which appears in a discharge in a tube is still called the Faraday dark space. Anyway, Professor Röntgen noted this effect. He published it, and he noticed, of course, which is the important point, that X-rays has a property of being able to penetrate matter. And very quickly, for that time, the medical profession took up this point, because here was the answer to Maiden's prayer to be able to look through the skin. So within the next 10 years, a very short time, when one looks at the conservatism of the medical profession then, and to some extent even now, a profession almost of radiography, certainly the science and practice of radiography had grown up, and X-rays had become relatively common. And now let me just show you what are the essentials of an X-ray tube. Here we have an evacuated glass tube. It has two electrodes sealed into it. This one here on this side, which is connected to the negative part of the high voltage supply, is called the cathode. And this other one on the other end is called the anode, connected to the positive supply. And if you apply a sufficiently high voltage across these, you drag electrons out of the cathode almost by brute force, and you get a stream of electrons passing across here and impinging with considerable force onto the anode. Now, it's one of the facts of physics that when you have high-speed electrons impinging on metal, that you generate X-rays. And the faster the electrons are moving, the more penetrating the X-rays will be, which are generated by this process. Now, we can't see X-rays, and therefore we have to use some other means of detecting them. But before I tell you how to detect X-rays, let's just see how they fit into the general electromagnetic spectrum of radiation, of electromagnetic radiation, because light and radio and X-rays are all of the same family of vibrations called electromagnetic vibrations. And let us look past some of the lectures we've already had. I think in the last lecture, I swallowed a radio transmitter. And this radio transmitter was transmitting, roughly speaking, on a long wave band and had a wavelength of 600 meters. The wavelengths in meters are down on a scale at the bottom here. So it would have come somewhere around here, between 100 and 1,000 meters on our scale, 600 meters. In the second program, when we talked about the Doppler effect, and I shone a radar set on you, I was using a radio wavelength of 3 centimeters. And this would have come somewhere in this part of the spectrum here, in the radar part of the spectrum. In the very first lecture, we were looking at carbon dioxide and its infrared absorption. Now, this is just this side of light, a wavelength of 1 micron, that is 1/1,000,000th of a meter, which would have come out here. And here, of course, is that relatively short part of the spectrum, which we call light, and which we can see. What we should be doing today is to talk about X-rays. Now, X-rays are still shorter than the violet part of the spectrum, and the harder the X-rays become, that is, the faster the electrons were moving, the higher the voltage which was applied to the X-ray tube, the shorter the wavelength becomes. This is all X-rays here. And later on, we should also be talking about gamma rays, which one can think really in terms of being very hard X-rays, even harder than those which can be produced by most X-ray tubes. Now, what can we do about rendering the X-rays visible? Well, there are two things. The first one is, of course, due to the accidental discovery of Röntgen and its predecessors, in any case, that photographic film can be blackened by X-ray in the same way as it can be blackened by light. And so you could create a situation where you might put an X-ray tube behind your patient if you wanted to X-ray his chest, and you could hold a photographic plate on the front of his chest. You could turn the X-ray source on, and because the X-ray source is virtually a point source, the bones and the other structures inside the chest would throw a shadow onto the film. Now, the important thing to remember here is this would only happen if the source was nearly a point. This would not happen, for instance, there's no, well, as it happens, there is a shadow because it's from the light up there. But if there was a large source of light here, I wouldn't be able to cast a definite shadow in the way which I'm casting a shadow here. So you can only get a really good shadow if your source is small. And the reason we get good shadows from sunlight, for instance, is because even though the sun is very large, it is a very long way away, and therefore behaves rather like a point source to us. So here we have a photographic film. This is one way of looking at it. The other way would have been to use a screen like this screen here, which is coated with one of a number of minerals, for instance, zinc sulfide and barium platinocyanide, which this screen happens to be coated with, share the property of glowing when X-rays strike them. Now, these substances are very closely related to those which coat the inside surface of your television tubes, because those substances called phosphors have the property of glowing when electrons strike them. The processes which go in them to excite them to fluorescence, as it's called, are very similar to those which occur on a fluorescent screen of this kind. So another way, therefore, of rendering the X-rays visible would have been to put the X-ray source behind the patient and a fluorescent screen in front like this, and then to watch the images on the screen. The trouble is that the images are very, very faint indeed, and one would have to adapt one's eyes for a long time and sit in a very dark room to be able to see them. Now, the next improvement in this, because at this stage, X-rays took a long time. The exposure might have been a few minutes or even half an hour, and it was difficult for a patient to keep still for all this time, and you certainly couldn't have looked at something moving like the heart because it would have been blurred. X-ray pictures were pretty fuzzy images, so they were already useful. And then there was a minor breakthrough in 1913, and I'll show you a slide of this. Whenever I show slides, I will now have to disappear behind some of these large pieces of apparatus. Professor Coolidge, or Mr. Coolidge perhaps, or Dr. Coolidge in the United States, improved the X-ray tube enormously by substituting a heated filament instead of the cold cathode. Now, if you make a wire red hot or even white hot, it emits electrons copiously. It surrounds itself with a cloud of electrons, and rather than having to drag the electrons out of a cold piece of metal by brute force, one now has a copious supply of them, which can be accelerated by the high voltage difference between the cathode and the anode. They will strike the anode, which is now angered in this way, as you see here, to produce a very much greater, very much more intense beam of X-rays. It's really just like having a much brighter light, because you've now got a larger number of electrons. Having shaped the anode in this way also helps to direct the beam in the direction in which you want it to shine, rather than being evenly distributed all over the place. So here was one way of shortening the exposures. The other way, which was, I suppose, equally important, was to realize that photographic film isn't, in fact, particularly sensitive to X-rays, because most of the X-rays go straight through it, in the same way as they go straight through other materials as well. You can't give the X-rays a pat on the back and say, I want you to stop at the film, having first gone through all the skin and bones and so on of the patient. So only a small amount of the energy is actually used to fog the film. Now, this is important because, to realize that the sensitivity of film isn't very high to X-rays. It's of importance for those of you who do a lot of flying and have your luggage pass through the X-ray detectors for bombs and guns and so on, that those which use relatively weak beams of X-rays or short pulses of X-rays probably won't affect your films at all, because the basic sensitivity of your film to X-ray is small. But the next development was to make use of the fact, or to combine the effects of the fluorescent screens, which I've already shown you just now, and the sensitivity of film both to X-ray and light, by sandwiching the film between two screens which are made of this fluorescent material. So that this film, in addition to being affected by the direct beam of X-rays, was also affected by the glow which was being produced by the so-called intensifying screens. And the combination of having more powerful X-ray sources, rather better films, and intensifying screens of increasing efficiency has now made it possible to take X-ray photographs in a fraction of a second, rather than many minutes or possibly half an hour. And that, roughly speaking, was where X-rays were before the Second World War. So, of course, I've glossed over a whole range of technical development. So the situation is that one was able to take photographs. One could do, with a great deal of dark adaptation, one could see things on a fluorescent screen. Just to give you some idea what an X-ray photograph looks like, I've got one here of, what do you think these are? Feet, right? A pair of feet. You can see the big. Well, it can't be a pair of feet, can it? Because the big toe is on the same side. Or can it be? No, not my feet aren't arranged that way. Anyway, you can see the big toe here, and the other toes. You can also see that the bones are not of uniform darkness, but that the inner part of the bone here on the film is darker than the outer side. Now this means that the inner part of the bone, which are presumably hollow, or certainly aren't made of anything like as dense, do absorb less X-rays than the outside. Because they absorb less X-rays, more reaches the film, and therefore more blackening of the film. This is, after all, just like the negative inside your camera. Anyway, as I was saying, the situation was one could take perfectly good photographs, and one could do fluoroscopy, as it's called, that is looking at a fluorescent screen, providing one was prepared to sit in the dark for a long time, and providing one was prepared to accept that the patient was going to get a fairly large dose of X-rays, because if one wanted to see the stomach moving, for instance, one would have to keep the X-ray beam switched on for all that time. And then there was another technical breakthrough soon after the war, which was called the image intensifier. Let me explain to you how this works. Here we've got the X-ray tube in a rather diagrammatic fashion, and imagine that the patient is in between here somewhere, in between the X-ray tube and the front surface of the image intensifier. Now, immediately inside the glass bulb of the image intensifier, we have a fluorescent screen, just like the screen which I've just shown you. So at this stage here, the X-ray image is translated into a light image. And if we could put our head inside this bulb, we would be able to see the glow, just as we might be able to see the glow on a fluorescent screen. But immediately behind this screen which can glow is a thin layer of a metal such as cesium or potassium. These are metals which can give out electrons when light strikes them. In fact, these are normally the cathodes of photoelectric cells. These are electronic devices which are sensitive to light. So we have, by this very close coupling of the fluorescent screen with our photocathode, we can now first translate our X-rays into light, and then translate our light into electrons. Now, one of the features of electrons are that one can focus them in much the same way as one can focus light. So we can focus the electron picture, which we have at this stage, onto a much smaller screen up here to produce a very much brighter image, because we've got the same number of electrons now striking a very much smaller screen. But in addition to that, we've been able to make the electrons go very much faster, because we've got a high voltage difference inside this tube, so that the picture which appears on this tiny fluorescent screen here can be between 3,000 and 5,000 times brighter than the picture which we started off with on this large screen down here. And hence the name of this device as being an image intensifier, because it makes the image brighter. We can then use a television camera to look at this tiny picture here, and once having got it on a television camera, we can make the picture appear on an ordinary television monitor, which can be viewed in broad daylight, or certainly in good illumination. So we've achieved three very important factors here. The first one is that we've taken away the need to sit in the dark for fluoroscopy, because we can now look at the image in comfort in a lit room. Secondly, the actual resolution which one can get on the picture, the fineness of the detail which one can see on the picture has been improved by this device. And thirdly, one can cut down to some extent the dose of X-rays which a patient receives. So there's three big advantages. Well, we have got one of these image intensifier machines here. And just to point out the major parts to you, the X-ray tube is inside here. It's surrounded by lead and other shielding, so that the beam of X-rays comes out of here. And the beam of X-rays is very accurately defined indeed, so that the X-rays, the whole cone of X-rays, all fall within this plate here, which is the front surface of the image intensifier, which I've told you about. And here is a television monitor on which the picture appears. Now, I'd like to call for my first jelly baby, please, to bring me the jelly. And this here is a red jelly. Thank you very much. Can you just go back to your seat, and I get you to fetch it in a moment. This is the red jelly, and it is a ball of jelly made out of gelatin, a double or triple strength, so that doesn't melt under all these lights, embedded in jelly which is just like it. So there's really no difference in the density between the red jelly and the light brown jelly. Now, if I were to put this onto the intensifier now, and we were to switch on the X-ray machine, would you expect to see anything on the screen or not, from what I've told you? Quite right. You wouldn't expect to see anything because there isn't, in fact, any density difference. And X-rays are absorbed the denser, the heavier in the whole the substance becomes. Let me just switch the X-ray on. Right? As you see, there's nothing to be seen. Thank you. So if you can now fetch your jelly back, and if you can now have the pink jelly baby to come and see me, please, and bring me her jelly. Thank you very much. And you also go back to your seat. On this jelly here, which looks much the same, it's pink rather than red. We've mixed a well-known brand of stomach powder in with the jelly, and this contains some bismuth aluminate. Now, bismuth is a fairly heavy metal, so it ought to absorb X-rays quite well. So we haven't actually put very much of it into here, so we would expect it, perhaps, to give not a very strong image. Let's see what happens with our slightly bismuth-laden jelly. Let's look at that picture. Right? Now you can see there's a thing about the size of a tennis ball. Can we just see it again? About the size of a tennis ball in the middle of the screen there, which shows up the difference in X-ray absorbing power between the jelly, which has a little bit of bismuth in it, and the surrounding jelly. Thank you very much. And this is a faint shadow which one might get from different sorts of tissue. Can you fetch your jelly back again? Thank you very much. Now let's look at some other things under this X-ray machine. I've got a clock here, and the clock has got a plastic back, which is of course not very dense, so I would not expect it to absorb X-rays very much. Not going. Better. And of course there are metal works inside, which one would expect to absorb X-ray, and there's a hand going around, and there are also some of the wheels going around inside. And I think this is always a rather pretty picture. I'll rest the clock on there, and we can switch that on. Now, if you look rather carefully, I get my pointer out. You can just about see the balance wheel moving there, and you can certainly see the hand going around. If you waited for rather longer, you would see some of the slower moving wheels moving. But you see very nicely the difference in contrast between the plastic back, which you can hardly see at all, the metal clips which hold the face on, the hand itself, than the works themselves here, which are very dense. Thank you. Let's just X-ray this harmless-looking loaf of bread. Now I'm going to put this onto the machine, and I just want you to look very carefully at the picture. Right, can we just now if I again point out on the monitor to you, it doesn't seem to be a uniform loaf of bread. There seem to be two things in it. It seems to have bones in it. Here you are. You can see two bones in my loaf of bread. Right? Now, what you've seen there is the shadow which the bones of the loaf of bread cast onto the fluorescent screen inside here. Now, what sort of picture would you expect if we were to cut the things through here? Just think about this for the moment. And Giles, will you just come down? And I've got a bread knife here. I take my pointer out of your way. Giles, I want you to cut a nice thick slice out of this loaf of bread. And you think of what sort of picture you would expect to see from this operation. Must have gone stale during the day. Giles sawing away. Right? Well, cut a nice slice. Cut it again. Cut it again there. Well, a bit thicker. Doorstep size. Right? Right? And now let's show it. Just come stand by the side of me, Giles. Let's show it to the camera. Now, is this a kind of picture which you would have expected? Yes? Now, thank you very much, Giles. You can go and eat it if you like. It's marzipan, actually. I spent yesterday evening with an apple corer making holes into a loaf of bread and then stuffing them with marzipan, not being quite sure that marzipan would actually show up on X-ray, but it apparently does. Now, what you see here is an entirely different view. Instead of being a shadow graph, this is a slice. And a view of this kind is actually called a tomogram. Now, the derivation of this word is that tomos is Greek for slice. So a tomograph is really a device for drawing slices. The last thing, I'll actually put my hand on there. Here's my hand, and you should be able to see the bones in my hand, just as you saw the bones on the X-ray photograph I showed you earlier on. Right? Can we switch it on? There we are. You can see all the bones and the joints on my hand. I wriggle my fingers. And I move my hand further down. You can see the bones of my wrist rather nicely there. You see how complicated my wrist is really made, out of how many little bones my wrist is made. And one of the beauties, of course, of an image intensifier of this kind is that you can see things in motion. If you just cast your mind back to the gastroscope, which we had in the last lecture, the tube which you could feed down into your stomach or into your intestines, if it has to take a very complicated route, one might well use an image intensifier of this kind to help one guide it around all the corners, because one could then not only look down it, as we were doing, but one could also see where the tip was and what sort of corner was coming next. So one could bend the little tip in the right direction in anticipation. This is really a very useful piece of machinery, and it is sufficiently mobile and can be moved around to be used, for instance, in operating theaters. It doesn't necessarily have to be used statically inside the X-ray department of a hospital. That's all I want to say about X-rays. And then I want to go on to a different form of energy, which can also be used to form images inside the body, called ultrasound. Now, you've already seen me use ultrasound on one occasion, but in that occasion, we were using it to measure the velocity of blood inside my aorta. Now we are going to use it to actually form a picture. And just to introduce you into this, I'll have to climb around here. Just let me. You might be surprised at the amount of equipment which we've got in here, but we barely could get it into this into the theater. There's something like 100,000 pounds worth here for your delectation, and I believe it's hardly ever been as crowded as this before. Now, what I've got here is, and I let you hear it, is a tiny loudspeaker, and this loudspeaker is producing very short pulses of sound. You can hear them now. Now, these pulses of sound are being reflected by that reflector which you see hanging from the ceiling, but they are almost equally well reflected by the ceiling itself. Now, if we know how fast sound travels in air, and we had a means of measuring how long it took the echo to come back again, we could find out how tall the Royal Institution was. Now, we can't actually make an absolute measurement of this because we haven't got the right sort of equipment, but what I'm going to do is to switch this loudspeaker on. I want you to be quiet while I do this in a moment. I'll tape record this, and then I play the tape back at 1/4 of the speed, which of course stretches out the time, and you should be able to hear the echo really quite clearly. So I'm now going to turn this on. I'm going to start the tape recorder. Right, I'll now turn this off again. I've got a tape recording. Turn the microphone down, the output up. I've got to reduce the speed now by a factor of 4. I have to put my glasses on to do this. Now I've got to rewind the let me just turn this. Right, and I'm now going to listen to this carefully. You can hear the bonk, which is a pulse taking off, and the echo coming back again. Right, now let's think of it as having been about 1/4 of a second. Let's say it was a quarter of a second. The delay between the pulse and the echo. I'm going to only make these figures up. And the 1/4 of a second was at 4 times reduced speed, so it would have been a 1/16 of a second in real time. Now, if sound travels at the speed of 1,100 feet per second, and 1,100 divided by 16 is how much about? It's about 70 or something of this kind. So the return journey from here to that reflector and back again would have been 70 feet, and we could have calculated from that the distance between here and the reflector would be 35 feet. It's probably something of that sort of order. So it's the guess of 1/4 of a second perhaps wasn't so bad. Now we can use this effect, this echo sounding effect, which is of course used by fishing boats to find shoals of fish, and by ships to find out how deep the sea is, and by destroyers to detect submarines because they give echoes in the water. It's a fairly commonly used technique. We can use that to investigate the insides of our bodies. Perhaps I try climbing around this way this time. It's rather easier to get around this way. And let me first show you how this can be applied on an inanimate model. I've got here a short perspex rod, and the perspex rod has got a flaw in it. It's got a saw cut in it, which is not complete. Otherwise, it would be falling away in 2 halves. But you can see the flaw there. I've got an ultrasonic probe here, which sends out pulses at a much higher frequency than the ones you heard just now, but nevertheless, the principle is the same. And you will remember me that when I used ultrasound on myself, I used a coupling medium because the sound doesn't like traveling, this high-frequency sound, through air very much. And I'm going to apply it to one end of this rod so that sound pulses are now going into the rod, being reflected by the imperfection and coming back again. And we're going to look at our now familiar cathode ray tube beam. And you see that there's a big dip at the beginning on the left, which is a pulse setting out. And then there is a peak about 1/3 of the way along the line, which is the reflection of the pulse. Now, if we had calibrated the time base in terms of centimeters of perspex, we could have found out how far away from my transducer the fault was. If I turn this rod around, because the cut is not in the middle, and use the other end, we ought to get the pulse, the reflection pulse, rather closer to the origin. I do this now. You see it's only about 2/3 away. That's the short end. This is the long end, the short end again. So we are now echo ranging the crack in this perspex rod. And this technique is used in industry quite frequently to detect cracks in castings, for instance. If you have large steel castings, which might be flawed, this is one of the way of finding it. But being a crack detector, we can also apply it to my head. Now, the reason for doing so is that I'm sure you've all seen brains at the butchers, that the brain comes as two hemispheres, and there's a groove in the middle of the brain. And this also ought to be able to give an echo. If I can bear to get enough of this goo into my hair, I'm now going to apply this just above my ear and see if we can pick up the pulses. I have to be able to see what I'm doing myself here to be able to do this. Let me put some more of the stuff on here. It's really only water. There we are. We've got one pulse coming up there. Now, the pulse which you can see there at the moment is not from the midline of my brain, but it's from the other side of my skull. That is a sound going straight across. And there's another little one coming up there now, about halfway between them. There we are, which is due to the midline of my brain. Now, if there's any fairness, if I apply to the other side, it ought to come at about the same place, shouldn't it? My brain is reasonably symmetrically constructed. And I'm going to try and do that. There we are. It's rather better on that one. The big dip at the beginning is the pulse setting out. The rather low little peak is probably the inside surface of my skull. We then get the midline of my brain, and the pulse at the far end then is a reflection from the other side of my skull. Now, I didn't just do this for fun, but this is in fact a measurement which is of some medical importance, because if somebody has fallen off a motorcycle and fallen on their head and injured their skull because they weren't wearing a crash helmet, for instance, there might well have been bleeding into the brain. Now, there's only a limited amount of space inside the brain, and therefore, if there were bleeding into one half of the brain, it would push the brain over, and it would displace the midline over to one side. So a fairly simple diagnostic test for this kind of thing would be to find out, exactly in the way which I've shown you just now, whether the midline has got itself displaced or not. Now, let me just show you one more slide. Let me get my pointer back. The kind of thing which was happening here just now was that we were sending a pulse into the rod. There was a reflection, and we were getting it back again. And we were displaying this as two peaks on a trace on a cathode ray tube. We could equally well have displayed it, not as upward deflections here, but having a dark trace which only became bright when an echo was being encountered. And this is, in fact, the way which is normally used to make a picture. Now, there's somebody called Alex in the audience who's going to help me with this experiment. We've got a piece of machinery here, a different probe, which is inside this tank of water here, which we can turn like this, so we can get it to look around itself, so that we can get a very large number of echo soundings, and which, if they're all put side by side in the appropriate orientation, we can actually get these to make a picture. Now, first, I'm just going to show you what happens in the empty tank here. Just empty tank for the moment. I'm going to turn this transducer around, and you can see the bright line in the middle, which is due to the pulse actually on the transducer, and then you can see the rim of this basin here. I'm now going to ask Alex to put her fingers into here, like that, And I'm going to do the scan again. Can we just wipe it off the screen? I'm going to do the scan again, like that. Right? And here we've got 4 fingers, which have been interposed. Now if you'd like to move them a little bit nearer, and let me do it again. There's the 4 fingers very close. If you go now, put them right on the edge. We clear the screen again. There we are. So we have now an image, which is again incidentally a tomogram, because we've got a slice through here. We've really got a slice through this tank, and there's happened to be 4 circles in the slice, which were just like my circles of marzipan in my slice of bread, which were due to the fingers. Right, thank you very much. Thank you very much, Alex. Now, the next thing which we're going to do is going to be the most difficult one, and that is we're actually going to try and get an image from somebody's inside. And I should emphasize here straight away that I'm not an expert at doing this. I made the same excuse when I demonstrated the gastroscope to you during the last lecture, but I hope to be able at least to give you some idea of how this works. We have got to change the machine around a little bit for doing this. If I could ask Timothy to come down. Timothy has a hard job in that he has to take some of his clothes off in a moment, and also that he's ticklish. And being ticklish is his greatest affliction. Right? You've got your shoulders down with this mark here. Now, what I'm going to do in a moment is to scan a line along his back, like that. Let me get it more or less in the right place. And I've got to, unfortunately, put a lot of this goo onto him. And it's cold, too. There's no specially pre-warmed goo. There we are. I can feel him squirming already. I'm now going to put this probe, which is a really very clever one, because you see this probe can rotate. It can also move in this direction, and it can move up and down. And the electron beam on the display always knows where it is, so that the bright and dark spots appear on the right part of the screen. Well, I'm now going to, I think I have to do this from behind here. I'm going to try and do a scan. I think you'll be able to watch this on your monitors. Right? Now, I wonder where I can point to this. If you look on your screens, this shadow which we've got here, I haven't really done this very well, but I think it illustrates the principle. This shadow is a shadow which is cast by a spine, because there's a big bone there which absorbs, which reflects the ultrasound energy very well, we can't see anything behind this. This thing here is almost certainly one of his kidneys, because the kidneys are around the back here, and you can just see the beginning of the other kidney had I scanned them a little bit more cleverly along here as well. I think I might just have one more go on this, see whether I can get a better picture. But I told you I wasn't very good at this. Just going to spread the goo around a bit more. Start right around here. I can feel him quivering underneath me. Right, it's a not dissimilar picture, again with one kidney being shown. Now, if you can find a towel to wipe you down, Timothy, I think you've suffered enough. Thank you very much. And if we can extract you from this, Now, there are two merits to machinery of this kind. The first one is that as far as one knows, ultrasound radiation, particularly at these very, very low intensities, is totally harmless to people or animals. So one can do this kind of investigation as often as one likes. Yeah. It is particularly used in obstetric work because quite a few years ago the decision was made not to X-ray expectant mothers because growing organisms are particularly sensitive to X-ray to X-ray damage. And this is therefore a tool which is used not infrequently to look at the unborn child in the womb of its mother. And this is probably used more for this purpose than for any other purpose. Right, and now so much for ultrasound. And I now would like to go to the third way of rendering structures visible inside the body. Now the two methods which I've shown you share the property that both of them use energy which comes from the outside. That in one case we used X-rays, in the other case we use ultrasound. I'm now going to make a picture in a moment which uses energy which comes from my inside. And to do so, do so, at 9 o'clock this morning, I was injected with a small dose, a very small dose, of a radioactive compound. It was injected into my bloodstream, and this particular radioactive material called technetium is attached to a chemical group which preferentially attaches it to my bones. So by this time, a good deal of it will have attached itself to my bones. Now, technetium was not an element which is found in nature, because it's only got a half-life of 6 hours, and even if there had been a lot of it when the Earth or the universe was first created, or the Earth was first created, they have an awful lot of 6 hours between then and now. It halves its quantity every 6 hours, so none of it is left. So it has to be made artificially from the decay of another radioactive substance now. Now, how can we detect this? Because even though it might be attached to my bones, if I were to just stand in front of a piece of film or something which was sensitive to this, we would get a completely confused image. Because unlike the X-ray case, the radiation doesn't all come from one point and cast a clear shadow. It's given off in all directions. Just as much, if I were to switch one of these bulbs on here, every one of you can see both the red light and this green light. If you were the piece of film, I wouldn't be able to, and you were sensitive to light, I wouldn't be able to locate the red light and the green light by exposing you to these lights. So one has to think of some other way of getting an image. And the technique which is used is known as collimation. Now, I happen to have a row of children in the front row here, and I've made a very crude collimator for them. And what I would like you to do is to lift this up, and each of you, without cheating, to look straight ahead down one of these tubes. Now, if I ask you, Timothy, which color light can you see? And if I ask you at the other end of the row, which color light can you see? The red one. And can you see the green light?
No.
And can you see the red light?
No.
And how about you in the middle? Which color light can you see? If you just peer straight down the inside of your tubes. Green?
Red.
Red. Right. So if the children had been the piece of film, we would now have known, at least with this very crude system, that the green light that the red light was on the right and the green light was on the left. Right. You can put your little peeping tubes down, and this way we've illustrated the principle of a collimator. Now, if I could have my next slide, here is a principle of the gamma camera. Here again is a slice of body. Here is a collimator, which I've just shown you, which could be holes drilled into a block of lead, so that any rays given off by the radioactive material, which were not passing more or less straight down the holes, would strike the sides of the holes and be absorbed. And behind this here is a slice of a crystal of sodium iodide. Now, large crystals of sodium iodide have the property that when a gamma ray strikes them, and it's gamma rays which are being given out by the radioactive isotope inside me, a flash of light is generated. So whenever one of these rays manages to get through the collimator, it generates a flash of light. Now, behind this slice of sodium iodide is a bank of light detectors, photomultipliers as they are called, and they're arranged in circles like this, and there are 37 of these in a particular machine which I will show you in a moment. Now, you might think that only having 37 of them would mean that we can only make up a picture made up of 37 points. But it isn't like that, because the electronics of this are clever, and if the flash, for instance, were to occur there, then it would be seen by this one, and that one, and that one, and perhaps to a lesser extent by that one. And by measuring the relative intensities of the flash as it is seen by every one of these photocells, one can calculate where between them the flash must have taken place. And one can then create a picture from that which actually locates the position of the flash correctly in that plane. Well, now let me introduce you to the machine which actually does this. This machine here is called a gamma camera, and it is constructed in just the way which I've shown you diagrammatically just now. Here is the active surface of it, and immediately behind this is a thick lead plate with 16,000 holes drilled into it, between 1 and 2 millimeters in diameter, which are the collimator, just like the collimator which the front row demonstrated just now. Behind that is the half-inch thick crystal of sodium iodide, and behind that are the 37 photomultipliers. And the whole thing is encased in a very thick lead casing, so as to avoid as far as possible rays getting into this from any direction other than the front. Now, just to start with, let's look at the natural background of radiation here, and it's being displayed on this little cathode ray tube monitor here, in which you can see a circle which is equivalent to the circle which you can see on the front of the gamma camera. And if you watch the Milky Way coming up on there, each spot which appears is one cosmic ray, one other bit of natural radioactivity impinging onto the gamma camera. You can see it building up very nicely there. Right? This is where another one of my jellies comes in, the jelly I've kept back. This jelly here has a ball inside it, which has also got a very small quantity of radioactivity in it. Now I'm going to hold it in front of this gamma camera. We can clear the screen again. If we watch this now, we can see that our Milky Way has suddenly got a sun in it, and a very bright sun in it. So we formed an image of the radioactive ball in the middle of this large, otherwise inactive jelly. Well, I told you that I had received a dose of technetium this morning, which by now should have gone for my bones. And if I stand in front of the camera now, we'll have to see whether we can distinguish any part of my skeleton. It's got to be adjusted to the right height. And if you watch the little screen when it becomes visible again in a moment. Right, now if you watch this rather carefully, you see a more intense region down the middle, which coincides with my spine, and two regions of high intensity down here, which are my pelvic bones, and nothing much here, which is a soft part of me where there aren't any bones. My ribs don't start here, and my pelvis stops there. It's really rather beautifully clear at the moment. So you can see that my bony skeleton has been outlined by radiation, which is not being put into me by something else, but which is being given out by my skeleton. Now, you might ask what this kind of thing is good for. Well, just to give you two possible applications, some patients suffer from something called a pulmonary embolus. This is really just a fancy name for saying that one of the blood vessels supplying part of the lung has become blocked up. If you suspect this, one of the things you can do is to inject a short-lived radioisotope into the bloodstream and then stand the patient or lie the patient in front of one of these gamma cameras. If there's no interruption to the blood supply of the lung, the whole of the lung will fill reasonably uniformly with the radioactive blood. If some part of it has become blocked off, you would see a hole in the brightness, in the bright blobs which you would see on the gamma camera. Another application would be that if you suspect certain kinds of cancer, for instance, the cancer of the thyroid has a property of being very much attracted to iodine, which may be circulating in the bloodstream. It takes out the iodine from the bloodstream, so that if you were to inject some radioactive iodine, a lot of it would be taken up by the thyroid. Now, if the thyroid had a cancer, and some of the cancer cells had broken away and been carried away to some other part of the body, then you would get an illegal piece of thyroid growing somewhere else, which would also take up iodine. And by scanning somebody with a gamma camera like this, you would be able to notice this, that here was some other part of tissue which was picking up the radioactive isotope. You would then know that here you had a secondary carcinoma. Now, you may have wondered what has happened to the technetium which was injected into me this morning. Well, technetium is principally excreted through the kidneys into the urine. I haven't been today since I've had my dose, and let's see where it's gone. Now, if we lower the gamma camera to my nether regions here, I think you can see a nice bright blob coming up there, about there, which is in fact where most of the technetium which isn't stuck onto my bones at present is. Well, I think I better go now. But before leaving the scene completely, could I just ask some of you to bring some bring your teddy bears with you for the last lecture in the series called Signals from the Mind. I won't tell you what the teddy bears are for, but I would like a few teddy bears, say 20 of them, with faces and full complement of ears, arms, eyes, and fur, for an experiment which I'd like to do. So those of you who have much loved and attacked teddy bears would like to bring them along with you and put a label onto them so we can return the teddies to their rightful owners, I'd be very grateful. Good night.